let's briefly discuss about electrical energy and power. Consider a simple conductor which is maintained at a certain potential difference between its two ends. So let this end be denoted by A and this end be denoted by B. So let's say VA is the voltage at point A and VB is the voltage at point B. So the assumption we are making is VA is greater than V of B, which means electricity I will move from the end maintained at a higher voltage to the end B, which is maintained at a lower voltage. Consider this analogous to a plank of wood which I maintain, the two ends of which I maintain at different heights. So if the plank is maintained in this position, point A is higher than point B. So if I drop a few drops of water at this end, we would expect the water drops to travel down to B. There is a simple reason being this point A is at a higher plane compared to point B. Analogous to that is this conductor. We have two ends of the conductor maintained at two different voltages, and the potential difference decreases as we move to B from A. So voltage at A is greater than voltage at B, which means our electric current is moving from A to B. If this is the case, then the total potential energy as the charges or electrons in this case move from A to B would be given by the final potential energy at B minus the initial potential energy by the charges at A. So what would be the potential energy at B or A? So at A, let's say I denote the potential energy at A as UA. The potential energy at A is given by the voltage at A multiplied by the charges. Similarly at B, the potential energy is VB multiplied by the charges. Assuming Q charges have flowed between A and B over a period of time delta t. So the assumption I am making is that I am allowing this potential difference to exist for a time period delta t, during which time period Q amount of charges have flowed from point A to point B. Now if this is the case, I put it here, VBQ minus V A Q, which is Q common VB minus VA. But we started off the discussion by stating that VA is greater than VB, which means VB minus VA is a negative quantity. So I get minus Q into the change in voltage. So I'd say the change in voltage as delta V. The change in voltage is delta V. So continuing from our previous discussions, the change in potential energy. The change in potential energy, let me denote it as delta U. We got it as minus delta V into Q. Now we also know that Q is a product of the current multiplied by the time for which the current has flowed, which is delta T. So I can replace this in the original equation. So my change in potential energy over a period of time delta T in the charges flowing from A to B is given by minus I delta V into delta T. Now we'll call this equation 1. What will be the change in kinetic energy? The change in kinetic energy during the same time delta T. Let's make an assumption here. Let's make an assumption that none of these Q charges that are traveling from A to B encounter any collisions, which means they travel absolutely unhindered without colliding with any ions. In that case, I can safely say that the change in kinetic energy should be equal to the negative of the change in potential energy. That goes because of law of conservation of energy. Now if I replace delta U with what I just got here, then this becomes delta K equals minus of minus I delta V into delta T, which is I delta V into delta T. But remember, we made an assumption. What was the assumption that we made? We assumed that none of the charge carriers, the electrons in this case, assuming it to be a piece of metal, are encountering any collisions. They are not encountering any collisions. With this assumption, this holds true. That is, the total change in kinetic energy is equal to the change in potential energy. But in real life, this is not true. For the simple reason that conductors are densely packed with atoms. When this is the case, every charge encounters a collision with an ion at an average collision time given by tau. So when there is a collision, what is happening? The energy being carried by the charge is partially being transferred to the atom, and this atom starts vibrating a little more vigorously than it was previously vibrating, and all these added vibrations of multiple layers of atoms causes an increase in the thermal energy. It will cause an increase in the vibrations, which eventually translates to increased thermal energy or the heating up of the conductor, which means this does not necessarily hold true. Yet another reason why kinetic energy is not equal to the potential energy in this case is the concept of drift velocity. If kinetic energy were equal to the change in potential energy, the total change in kinetic energy is equal to the change in potential energy, then it should also have been true that the electrons would have gone on accelerating infinitely till they reach the other end, which is not true because we have discussed the concept of drift velocity. Every electron reaches a drift velocity which is constant, which means the energy that would have provided them infinite acceleration has been taken up by something else. That something else is the atoms with which they have shared their energy and which these atoms are vibrating to cause an increase in the thermal energy of the conductor. So that means I can write that the total energy shared is equal to I V delta T, where delta V, I am replacing it with V because I assume that the voltage difference here between these 2 points, which is delta V, is equal to the voltage across these 2 points. So this is the kinetic energy equation we got previously, and this is also the work being done in transferring the energy to the atoms. Now if I take the total power that's being transferred to the atoms, that's also given by delta, work done by time. It is the rate at which work is being done. So if I substitute this over here, what I'm going to get is V I delta T by delta T. So delta T and delta T cancel out, which leaves me with P is equal to V I. The total power dissipated by a conductor which is maintained at a voltage difference of V, through which a current I is flowing, is given by this simple equation: P is equal to V into I, where P is power dissipated. This dissipated power is sometimes also referred to as ohmic loss. Ohmic loss, because this loss is due to the resistance offered by this conductor to the flow of electricity. So we know by Ohm's law V equals IR. So if I substitute this in this equation, I get another form of the same, which is P is equal to I R into I, which is I square R. This is yet another form of this equation. Similarly, I can also substitute I equals V by R, which is yet another form of the Ohm's law. Then I get P is equal to V square by R. These are the three forms of the power equation. There's a practical significance of this particular equation. We all know that power that we use in everyday life at our homes and workplaces is generated at power stations that are located hundreds or even thousands of kilometers away. And once this power is generated, this power needs to be transmitted as electrical energy over thousands of kilometers through cables, conducting cables and wires to the place where it would be eventually used. So this particular equation also gives us a way on how do I reduce the amount of power loss that happens when I transmit electricity over large distances. It's common knowledge that as power is transmitted, say from say the Jog power station at Sharavati all the way to Bangalore or Mysore or any other place in Karnataka where it would be eventually consumed in a domestic household or a workplace, these cables, though they are excellent conductors, there is a significant power loss because of the lengths involved, which can range from hundreds to thousands of kilometers. So how does one reduce these losses, if not do away with it entirely? So this equation again comes handy. Let's say at our household there is a device. There's a device with resistance R which consumes electricity I at a particular voltage V, and there's a power generating station located several thousand kilometers away, and electricity is transmitted via power cables which offer, let's say, a resistance RC. So the power loss in these cables, let's assume them to be PC, or the power loss in cables. Now basically on this equation I can write that my power loss due to these cables is I square RC, because there is current I flowing through these cables and the power loss is a square product of I with the resistance offered by the cables. But I can also write a similar equation here which says The power of this device is given by V into I, or I is equal to P by V. Now the current is the same, so I can substitute this over here. So which gives me power loss in the cables as P square by V square into RC. So what we see here is an inverse relationship between the power loss in the cables to the voltage being consumed at the household level, which means to reduce the power loss due to the cables, we have to carry enormous voltages across these lines, which means to say the voltage between this point and this point must be very, very high, so that the loss due to the cables, the resistance of the cables, the loss in power is minimal. Which is one reason why you see in everyday life the high tension cables. Once you cross city limits, you get power cables which are hoisted at extended heights beyond the reach of ordinary heights. And these high tension cables are mounted on high tension towers with clear markings saying dangerous high voltage. They carry current in the range of 35,000 volts to 50,000, sometimes even 60,000 volts. The simple reason being, the greater this number, the lower the loss of power in these cables. Then what happens at the end? Do we end up using our devices at the same voltage? No, it's not possible, because at such high voltages, our regular devices would cease working. They'll just end up in an explosion. So at the end point, we have something called transformers. These transformers reduce the voltage from 50,000 volts or 35,000 volts to a much more usable 220 volts. So using a step down transformer, we reduce the voltage from 50,000 volts to a more usable 220 volts. So this is yet another way how the power equation helps us reduce losses due to electrical energy transmission over extended lengths or extended distances.